Hurricanes. Floods.
We are on evacuation warning.
Fires. As global warming heats up the planet, the weather's getting even wilder. Now, some of our smartest scientists are fighting back, creating new technologies to tame Mother Nature. From amazing new tools to monitor storms.
As a scientist, I'm driven to study the most violent storms on Earth.
To high-tech barriers that keep our cities from flooding.
20-foot storm surge is very, very serious.
Even robotic ships and satellites to put global warming in reverse.
The ability to deal with carbon dioxide is now within our grasp.
Controlling the weather and changing our lives. That's ecotech. East Texas, summer 2007. A terrible flood is swamping the region.
It's a wonder we're alive. It's a wonder that we lived through this.
At the same time, just a few states away in California, they're suffering the opposite.
We need the rain.
Forest fires.
It's heartbreaking. It's a helpless feeling.
Bigger hurricanes, bigger mudslides, bigger floods. Extreme weather events have become more shocking and more common. And many scientists believe the problems can be traced to climate change.
As there's more heat in the atmosphere associated with global warming, there's more evaporation, and this provides the fuel for all of the storms, including hurricanes.
More water vapor and warmer sea temperatures are already causing bigger, badder hurricanes. That's bad news for most of us, but Joshua Werman doesn't mind.
I'm Joshua Werman, and I'm a meteorologist. I've been in 9 different hurricanes. I observed 130 different tornadoes.
But don't call him a storm chaser.
I don't really like the term storm chaser because that really doesn't describe what we do. A lot of times we get in front of the storm and wait for it to chase us. Other times we're just waiting all day watching for them to form. We're researchers. We're studying how the storms form, how they mature, and how they die.
Understanding how warmer air and warmer waters contribute to a hurricane's power is critical for climate scientists. And Werman gets a ringside seat when he drives into the storms.
Okay, Dow 2, we're on the move again. We're just looking for a place to deploy.
He uses his own state-of-the-art technology to get the job done.
This is the Rapid Scan Dow. It's the newest generation of Dow, and it has 6 simultaneous beams. I go swish, swish, and I can get a complete 3-dimensional image all the way up into the cloud in about 5 or 10 seconds. Anything that's out there, we can get closer to and literally see tens of thousands of times more detail. I can discover new things about those storms, new things about how they do damage and how to forecast them better.
Werman invented the Dow, or Doppler on wheels, himself. It uses a Doppler radar system, which sends out beams of radio waves that reflect off rain, dust, and other objects in the air to measure their velocity. But Werman's made a few improvements.
Inside here is some very delicate hardware, and it consists of 100 rectangular pipes, waveguides, each one of which has 100 very carefully cut slots to about 1/100 of a degree. So there's about an array of 10,000 of them, which then can direct the beam in different directions. Inside this box, we have a big radar transmitter. We have to make very high-intensity microwaves to send out the antenna, because we need to send out an intense signal because the clouds really don't reflect much back. So we send out a strong signal, and we get a very, very weak signal back. We have hydraulic leveling feet. We need to be very stable. Otherwise, the buffeting effect of 100-mile-an-hour winds in a hurricane would just mess up our data, would make our beams jiggle back and forth.
The newest Dow is still a work in progress. The design builds on Werman's many years of experience driving into storms.
What I'm standing on is an auxiliary gas tank. These trucks go through a lot of gas. We basically get maybe 5-6 miles a gallon, and we're driving around in very remote areas, and I've learned from experience that it's bad to run out of gas. Then we can't run away.
It's all part of a lifestyle that may be a little difficult to understand.
To people who don't do this, going into hurricanes seems very, very dangerous. But even though we're playing very, very close to danger, We're aware of where it is, and we're aware of how to stay safe and get away from it when we need to.
Werman's data pays off at scientific institutes like the National Center for Atmospheric Research in Boulder, Colorado.
We're learning a great deal from these observations, and we can put that into models, improve our models, and ultimately improve our predictions.
For Kevin Trenberth, the most important thing to figure out is how a warmer Earth and warmer ocean will change hurricanes. It's a complex subject.
When the heat goes into the ocean, what we expect is that it will make more intense hurricanes, but then a bigger hurricane takes much more energy out of the ocean. And that's why we don't expect that there's going to be an increase in the total number of hurricanes, but what we expect is that there will be an increase in more intense storms.
Trenberth says the 2005 hurricane season, shown in this satellite time-lapse, is a sign of what can happen.
Sea temperatures were at record high levels. An analysis that we've done suggests that about half of that warmth was due to global warming. There was plenty of fuel for the storms, and they just kept coming. So this may well be a harbinger of the future, more activity of this nature.
But some scientists aren't so sure.
No smirking, Eric.
We see these swings back and forth lasting about 25 to 40 years. And what we think is going on is that this is a result of a natural oscillation in the Atlantic Ocean as well as the atmosphere above.
Chris Lancy is skeptical that global warming will cause either more storms or much stronger storms.
When I'm asked, are they being impacted by global warming, I think the answer is yes. But that's not the important question. The real critical one is by how much. Hurricanes today are probably stronger due to global warming, but on the order of 1%.
But even slightly stronger storms, coming on top of rising sea levels, will pose real threats to people and property. To protect them, forecasters need to make accurate predictions.
We've done a very good job of track forecasting, knowing where it's going to go, but we've had a lot of difficulty in making a good prediction of the intensity. Currently, our predictions really are only skillful out for about 2 days. And after days 3, 4, and 5, it's really a guess, and it's not a very good guess.
Unless we understand how hurricanes interact with the ocean's surface, the lowest levels in the hurricanes, we can't understand how they intensify rapidly and how they weaken rapidly.
Satellites can capture the upper layers of a storm, but they can't see the crucial area between the storm clouds and the ocean.
The challenge, of course, is that it's a very violent environment. We certainly would never send a manned aircraft into that area because the plane might crash.
The planes that we fly, the manned aircraft, typically fly about 2 miles above the ocean.
Joseph Sion at NOAA's Hurricane Research Division thinks he has the answer: an unmanned aerial drone called Aerosonde.
We're using this platform to see things that we've never been able to see before.
But just look at it.
It's roughly 9 feet across, about 28, 29 pounds. And that's with fuel. It's not very impressive as far as its physical dimensions, but it can do quite a lot. When I first started it a year and a half ago, people told me I was crazy. This is literally what makes the Aerosonde go. It's 24cc engine that's fuel injected. It's a small, very complicated lawnmower engine, really. We literally strap the Aerosonde to the roof of an SUV. We have a cradle there that allows the Aerosonde to stay put up until about 55 miles per hour. The Aerosonde then would take off and is controlled by joystick. Sort of like when you were a little kid, your remote control aircraft, it's the same thing. A little more expensive, a little more technical, but the same concept.
With the help of NASA and other agencies, Sion flew the Aerosonde into Tropical Storm Ophelia in 2005.
It appears from the data that this thing not only went up and down, but was backwards, sideways, upside down, and then within a matter of time, it righted itself.
The Aerosonde is able to avoid the worst turbulence in a storm because it's so much smaller than most aircraft. It glides on the windstream into the center of the storm, where it can help forecasters understand how strong the winds really are.
The platform that measured the strongest winds, which is what the Hurricane Center cares about, was the Aerosonde.
Because of its success in Ophelia, Aerosonde was cleared to fly into more storms in 2007. Texas in the summer is usually dry as a bone. But not in the summer of 2007. 44 freakish days of rain, including 19 inches in one 8-hour period, flood the eastern part of the state. 13 people are killed, 5 are missing.
Everything just messed up.
Floods during dry season. Could this be a sign of global warming? Many scientists believe it is, and they're scrambling to find new technologies to hold back the waters. The Army Corps of Engineers is trying to prevent disasters like the one in East Texas, testing state-of-the-art technologies to shore up levees and keep rivers and lakes from overflowing. The Rapid Deployment Flood Wall is one of them.
The Rapid Deployment Flood Wall is like Legos for adults, because all you have to do is connect them side to side and stack them. It takes 7 people 1 hour to build a 100-foot long wall, 4 foot high. It takes 35 laborers 20 hours to build a sandbag wall that's 100 feet long. We're 100 times faster than sandbags.
Faster and stronger. In tests, this lightweight grid withstood 40 hours of pounding waves. That's 72,000 waves. Al Orlanis invented the flood wall, which is made from a clear, reusable plastic. It's based on a very simple idea.
If you get a paper cup, turn it over, cut the bottom out, place sand inside the cup, you can stand on it because the sand builds compression.
Compacted sand and water are what give concrete its strength. Al took that strength and transferred it to a temporary wall that can hold back overflowing rivers or explosives. That's right. The military is using the flood wall to reinforce bunkers in Iraq. At home, the idea is to stockpile the walls for use in future floods. But compressed sand won't staunch the tides that threaten one of the best-known harbors in the world.
With rising sea level, climate change, much of New York City is low-lying. It's on the water's edge, built right at the water's edge.
Stony Brook University's Malcolm Bowman worries that the city can't handle the higher seas of a warmer Earth.
We can expect the sea in New York to be as high as 2.5 feet higher than it is now by the year 2050 or 2075. This may not sound like much, but a 20-foot storm surge on 2.5 feet sea level rise is very, very serious.
Most tunnels and subway lines would be flooded, as they were in August 2007. And Manhattan would be split at Canal Street, cutting off the financial district from the rest of the city.
This is not alarmist thinking. We get nor'easters every winter. We get hurricanes every fall. If we get a direct hit on New York City here, at high tide, the flooding could be extensive.
So Bowman has come up with an audacious plan to save New York City, if only someone would listen.
We would need at least 3 barriers to protect the city of New York and a 4th barrier to protect Jamaica Bay and Kennedy Airport. One would be at the main entrance to the harbor here at the Verrazano Narrows. The second one would be behind Staten Island to stop water leaking in from the ocean. And the third would be up near the Throgs Neck Bridge in the Upper East River, which is the connection of the harbor to Long Island Sound.
The city of London, England has had its own storm surge protection since the 1980s. The Thames Barrier is open most of the time to allow shipping traffic. The gates only close when a storm is on the way. Bowman envisions something similar for New York, but on a larger scale.
The barriers would have to be 45 feet above the water level. If you look at the bridge, the roadway of the bridge is probably 250 feet above the sea. So we're talking about 1/4 of the height between the sea and the roadway.
It's a big solution, but Bowman thinks there's no smaller way to deal with the new realities of a warming Earth. He's presented the plan to New York City, but the high cost scared the city fathers off.
Well, we're costing $1 billion. It's a large undertaking and would be certainly the largest civil engineering project in the United States.
But New Amsterdam can look to Old Amsterdam as a model of how to plan big to stem the rising tides. In the Netherlands, flood protection is massive. Just look at the behemoth Maaslandkering. When the North Sea rises 10 feet above its normal level, the barrier's base floods with water, and 2 locomobiles push the curved gates toward each other.
It more or less blocks so that the North Sea water
cannot flow into the hinterland, and our 5 to 8 million people are protected from the storm surges. My name is Pier Vellinga. I work at Wageningen University studying climate change. Sea level will rise and rainfall will become more intensive, and our river will come with peak discharges 20 to 30% higher than the present dikes can withstand.
The Netherlands is a delta, facing the onslaught of the sea and rivers flowing from Germany and Belgium. It's probably the best protected delta in the world, but now climate change poses a new threat.
The major challenge is whether we will be in time to redesign our country and our water systems.
Holland's first line of defense is on its coast. In a round-the-clock operation, ships pump sand onto sea beaches to keep the shoreline from eroding. It's messy work, but guided with scientific precision. The scientists at Delft Hydraulics have recreated a North Sea beach in a 160-foot-long flume, where they can study how tides move the sand.
What you see here is actually a scale model of the movement of waves, and the waves affect the sand below them.
The model helps them determine exactly where to place the newly dredged sand so it's not washed away. For more theoretical work, the hydrologists use computer simulations.
These computer models typically simulate what-if scenarios. If the dike would break at a certain moment, when the water is very high in the river or in the sea, what would happen? What you see here is a major break of the sea defense of the Netherlands in the western part of the Netherlands. This is The Hague and this is Rotterdam.
This flood is strictly hypothetical, but the model demonstrates a new reality for the vulnerable Dutch. Simply making dikes higher will not be enough in the age of global warming.
We may have to accommodate more water, and a bigger part of our country will have to be open water.
A project called Room for the Rivers is already clearing and digging out farmland to give the waters of the Rhine a place to spill out. But with some new houses, builders have taken a radically different approach.
When the water comes, the house will go up. Hello, my name is Gert Kengen. I'm the designer of these houses here.
These houses are built on the riverside of a dike. They rest on the ground, except that is, in the event of a flood.
The idea is that the water can go underneath here, and then it lifts up the whole structure.
Plumbing and electrical connections are all fed through flexible pipes, so the house can rise up to 18 feet. That's as high as the river would get before it overtopped the dike.
And here you see how we take care that the house stays in its place. It goes up and down alongside these big poles.
Amphibious homes which float only in floods, and homes that always float could give rivers room to run and people a place to live.
We're now speaking about a concept called hydrometropolis, so a real city in the water. And if you look at the Netherlands from a satellite 100 years from now, I expect that you see lots of water, and here and there you see a floating city.
It was only after a major flood in the North Sea in 1953 that the Netherlands and other European nations began building their storm barriers. There are similar projects being built near Venice and St. Petersburg, Russia. In New York, Malcolm Bowman hopes their example can be a lesson for cities facing the rising seas and extreme rains of a warming Earth.
Even though the threat may seem distant, we should start looking at the engineering designs, looking at the oceanography. We should start doing that now.
Summer 2007, the least rainfall ever recorded in Southern California, only 3 inches in a year. It seems that global warming not only causes floods, it causes drought.
What we find is that there's more precipitation occurring over the ocean instead of over land. And so drought is one of the big consequences.
With higher temperatures, more evaporation, and less rainfall, it looks like much of the world may experience drought. Some places already are. The western part of the United States has been in a drought for the past few decades, and climate models suggest that it will just get worse. And where there's drought, there's fire.
We didn't have any time at all to grab anything.
The U.S. had 96,000 wildfires in 2006, 45% more than the year before. At the Forest Service's Fire Research Divisions in Missoula, Montana, researchers are looking for answers. That means some people get paid to set fires.
I'm Lance.
I'm Bob. We test fireland chemicals that are used to suppress wildland fires.
Ready.
Flame on.
In this test, half of the flammable bed has been treated with a fire retardant. It uses a fertilizer salt that reacts with cellulose to lower the fire's temperature and intensity.
Approaching retardant. The retardant has reduced the flame heights to about 1 foot maximum when they had been burning at about 3 feet. You reduce the rate of spread and the intensity of the fire, then ground personnel can get there and hopefully control the wildfires before they spread.
Fires are the most spectacular effect of drought, but there are other problems on the horizon.
You know, Ben Franklin said the value of water is not known until the well runs dry.
Engineer Robert Renner heads a foundation researching better ways to provide safe and affordable drinking water.
Population projections show that 40% of the U.S. population is going to be in the states of California, Texas, and in Florida, and all those areas are relatively water-poor states.
Even in a drought or the middle of a desert, there's water available. But most of it is brackish groundwater, salty and undrinkable. A new technology may change all that.
We're bringing in brackish groundwater and making it drinkable. To do that, we have what's called the reverse osmosis process. I'm Ed Archuleta. I'm the general manager of the El Paso Water Utilities Public Service Board, and this is the largest inland desalination plant in the world.
This $87 million plant opened in August 2007. When it's fully operational, it will provide 27.5 million gallons of water a day to the people of El Paso and the Army personnel at Fort Bliss. There's plenty of water to work with. You can't see it, but there's more than 10 trillion gallons of groundwater available under this desert.
There is a tremendous amount of brackish water here, and up until recent years, the technology or the costs were just not there to develop this water.
The new technology is these filters.
Each one of these vessels here has 7 of these units that are basically joined side by side. This is the heart of the process.
The water is pumped through these cartridges, made from special membranes wrapped into tight spirals. The membranes have microscopic pores that act like doorways, stopping the combined salt and water particles from passing, while the smaller water molecules can squeeze through.
The key to this technology is the energy it takes to pump water through the membranes.
As the membranes have improved, the energy required has fallen. Reverse osmosis now takes half the electricity it did 10 years ago. That makes the desalination plant cost-effective for El Paso.
We figure that this plant, on capital plus operating costs, is going to deliver water at about $1.60 per 1,000 gallons.
For what you can buy a 1 gallon of bottled water for, a typical utility would produce 1,000 gallons.
But once they make the brackish water drinkable, what happens to the highly salty residue called concentrate? At seawater desalination plants, the concentrate can be pumped back into the ocean, but that won't work in the desert.
We look at evaporation. There's a lot of land out here, so you could build evaporation ponds, but we'd have to have about 700 acres of ponds.
The answer was a technology from the oil and gas industry called deep well injection. The wastewater is pumped deep below the earth, where it can be safely stored. The El Paso water utility found the right place to store the water, here, 22 miles from the desalination plant. It won't work everywhere.
El Paso was very fortunate to have a perfect geological formation that lent itself to deep well injection. All right, that's a wrap.
Okay.
We're sweating.
Clean drinking water will be a critical need in extreme drought, but it's not just water that will be scarce.
We rely on moisture to grow crops, and so there's potential for widespread famine.
What are we going to eat when drought dries up our land?
This corn loves hot, dry weather. I'm Jacqueline Hurd, and I lead a research team that's interested in developing drought-tolerant corn.
Farmers are planting more corn than ever before to feed people and animals, as well as to supply the ethanol industry. But in the last decade, drought has taken a major toll on the crop.
Well, this is the most disastrous beginning we've had.
Under drought stress, plants will typically shut down. They'll shut down their metabolism. They won't be able to capture the energy from the sun as efficiently.
Jacqueline Hurd's team at Monsanto wants to breed a type of corn that can grow in these conditions.
We're looking for varieties that are more adapted to drought-stress conditions, and then we actually supplement those varieties with a gene, a single gene that can actually positively impact the plant's performance.
The gene alters the corn plant so it can perform photosynthesis with less water. It's science on the smallest scale.
We use a process that employs a harmless bacterium, agrobacterium. It's a very natural process where the microbe actually inserts the gene to the 60,000 other genes that are in the corn plant.
A portion of the DNA from the agrobacterium binds with the plant's DNA. Once the microbe has done its work, the team starts field tests, literally.
We're in the middle of a drought trial, and it's really important that we tightly control the amount of water that's available to the plant. And so we use these soil moisture sensors, and we can monitor how much water is being depleted on a given day to know how much the plant is actually taking up.
Then they compare the plants as they grow.
So this is a well-watered plant that we just took from a plot down the way, and these are plants that had probably 4 to 6 inches less.
The plants with the new gene seem to be holding their own.
We've seen consistent yield advantages of about 10%. And what that means at the end of the growing season is that the plant is able to produce more ears under these stressful conditions.
Superstorms are hitting our coasts. We're deluged by water, or we're parched by the lack of it. Climate experts say all these weather events, from flood to drought, are linked to global warming. They're creating sophisticated models of the Earth's climate to determine just how fast the planet is heating up and what that means for our weather. The models are produced in supercomputers, but they're based on real-world data. To get that data, scientists are taking the latest technologies to the ends of the Earth.
Take her back up to 10 knots.
Here, in the Arctic Ocean, scientists aboard the icebreaker Louis S. Saint Laurent are testing how warm these icy waters are getting.
The Arctic is the heart of climate change. If there's any place to go to observe the warnings of climate change, it is to the Arctic.
Eddie Carmack is a climate research oceanographer and one of the leaders of this expedition in July 2007.
We want to understand the processes that are going on. It's not enough to sit back and philosophize about it. We have to get out and make measurements. That's why we're on this journey.
The icebreaker is loaded with equipment to test everything from the salinity of the water to the presence of the tiny sea creatures that keep larger animals alive.
Brittle star right there. Brittle star, yep. Beautiful.
This rosette, as it's called, can take advanced readings as well as sea samples from any depth. Monitoring this remote ocean is critical to understand how the entire planet is changing.
A warming of the Arctic, a retreat of the ice cover, could shift rainfall patterns northward, leaving the western United States with less rainfall than it would like to have.
In other words, what happens to the ice here is connected to life thousands of miles south. And what happens in the clouds has a direct impact on life on the ground.
We want to understand how people are affecting the climate. It's really the water vapor in the clouds that are doing most of that warming.
NASA's Brian Toon is the lead scientist of this intrepid band in the jungles of Costa Rica. It's another place where real-world data is being collected for the climate models that will help us understand how our weather is changing. At the same time that the icebreaker plies the Arctic Ocean, this group is probing the heavens.
There's a lot of things we don't understand about clouds. and water vapor in the upper atmosphere. But when you look from the top of thunderstorms, you see this rising column that the air goes up in. And that air is rising at speeds that are faster than an airliner can climb.
Clouds, particularly the thunderheads over the tropics, move visible pollution or aerosol particles through the atmosphere. These particles reflect sunlight, so figuring out how they move and how quickly they disperse is key to understanding how much hotter our planet can get.
What we're hoping to see in this mission is whether those short-lived compounds are actually being washed out or whether a convective thunderstorm can take them and push them upward into the stratosphere.
So NASA's researchers will collect data where no one has been before, in the clouds above Costa Rica. They've brought an impressive assortment of technology with them.
This plane has a large number of instruments on.
We have the MODIS Airborne Simulator. Basically, it's an imaging spectrometer.
I'm with the Cloud Physics LiDAR, which is CPL for short, and it's housed in this pod here.
Down underneath, there's a little drop tank there. That's called scanning HIS. So we're using almost every square inch of the plane to make measurements.
These instruments on the high-flying ER-2 will measure the cloud's properties from above. They'll combine with another suite of sensors in a modified DC-8, a sort of flying laboratory.
One can look from below and one can look from above.
But that's not all. The plan calls for multiple scientific platforms, from satellites in space to high-altitude aircraft to a weather balloon in formation, lined up directly below one another. As aerosol particles travel up through the clouds and disperse, this array of vehicles will measure them at every elevation. Dave Wright is the pilot for the ER-2, NASA's version of a U-2. He's got to be prepared, because even though it's steaming on the ground, where he's going is just the opposite.
They can get down to 130 degrees below zero at 55,000 feet here.
Whenever you're ready, Dave. Whenever you're ready.
After preparations in the pitch dark, the sun is rising and it's go time. The scientists on the ground can watch the data coming in real time.
Look at that shield right there. It's actually topped out.
After a smooth 5-hour mission over Panama and the ocean, the ER-2 returns.
Thanks, Dave. We flew over the tops of these big thunderstorms, and we flew directly over, one poking up to 50,000 feet, the pilot told us. And that's just great science data. So we've got a lot of work ahead of us. The work really only begins now when you begin to try to analyze what you've got.
Their work will go directly to another breed of scientists, the climate modelers.
I'm Ken Caldera. I'm a climate modeler. We don't build physical models of the planet, although that would be more fun. We have computer models, so we represent the Earth mathematically inside of a big computer.
All of the real-world measurements taken by the teams in Costa Rica and the Arctic, as well as satellite data, are fed into the modeler's supercomputers. There, the material is turned into physical and mathematical equations.
So what we do is we divide up the globe into a latitude and longitude grid, but then we also need to describe what's going on in the upper levels of the atmosphere. We have an ocean model going all the way down to the bottom of the ocean. We have a separate component that describes all of the characteristics of the land surface, interactions with plants, soil moisture, and we have one more component, and that's sea ice. We're constantly pushing on the boundaries of supercomputer technology to allow us to include as much complexity as possible.
Using real-world observations and computer predictions, the climate scientists can figure out what's already happened and what may happen in our warmer future. Their findings are startling.
Temperature zones are moving from the equator towards the pole as the Earth heats, and these temperature bands are already moving north about 30 feet a day.
In other words, it's getting warmer in places it shouldn't, like the North Pole, where the ice is melting. Climate scientists believe that the Earth will be 2 to 4 degrees Celsius warmer by the end of this century. That may not sound like a lot, but it can make a major difference.
It turns out that global temperature change
of 1 or 2 degrees is a very large change for the intensity of weather patterns and potentially the intensity of storms.
Our weather has already changed as a result, setting off a scramble to find technologies to meet the challenges of a warmer Earth. Our planet is heating up and throwing more extreme weather at us, but there are some scientists out there who think they can change the weather by actually reversing global warming.
I am Klaus Lackner, the inventor of synthetic trees.
Klaus Lackner is a geophysicist at Columbia University. He's teamed up with Alan Wright at Global Research Technologies in Tucson.
I'm kind of the wrench turner guy.
Together, they've created this machine. It may not look like a tree, but it's designed to do the same thing: absorb carbon dioxide from the air.
The wind comes in carrying natural and man-made CO2, and the air coming out has been scrubbed of much of its CO2.
A 40-foot container-sized module will capture a ton of CO2 in a day. So one of these modules will do in one day what the average tree is going to take a century to do.
The secret is in the material in these sheets or leaves. It's a secret Lackner and Wright won't reveal.
The material you see in here is a proprietary material we have developed for the purpose of collecting carbon dioxide. It has an affinity to CO2, but at the same time, this material doesn't bind the CO2 so tightly that it couldn't be easily removed.
As the air moves through this thing, and over time that panel gets fully loaded with CO2, and then we're ready for a wash cycle.
The liquid you see is a sodium carbonate solution.
The fluid wets all those sheets and runs down and is collected at the bottom of the system in a tray.
The wash solution goes into a salt splitter, which separates out the carbon dioxide. This prototype of the synthetic tree is smaller than the units Wright and Lackner want to build.
We're looking at a module the size of a 40-foot shipping container. In 6 days, one of those units could collect the carbon dioxide that the normal automobile would produce in a year's driving.
But there are a lot of cars on the road, so they want to build a whole lot of trees.
30 million of those could collect 10 billion tons of CO2.
Lackner and Wright imagined parks of these trees. They hope to eventually pump the carbon dioxide they produce deep underground, where it will be safely stored. But that costs money. So in the meantime, they'll sell the CO2 to oil companies. They pump the gas into underground reservoirs, where it expands, pushing up more oil into depleted wells.
In the short term, we have the ability to inject it into oil wells, and at that point, the CO2 actually has value.
They got the idea of selling to oil companies from another carbon capture technology called carbon sequestration. CO2 is captured at power plants before it's emitted into the air, then piped to oil wells.
If we're going to continue to use fossil fuels as the main source of energy, then we're going to have carbon sequestration.
But carbon sequestration will not reduce the greenhouse gases already in the air, or reverse the extreme weather they're already causing. Scientists looking to tackle that challenge have come up with some out-there ideas, grouped under the umbrella term geoengineering.
The basic idea of geoengineering is to deflect sunlight back to space, to cool the Earth, to compensate for the warming effect of greenhouse gases.
One of these schemes is being hatched at a lab in Scotland by a pioneer in generating energy from waves.
My name's Stephen Salter. I'm a retired professor of engineering design at Edinburgh University. At the moment, I'm concentrating on trying to put global warming into reverse.
Salter wants to do that by spraying a mist of seawater into low clouds over the ocean.
It's not quite as salty as seawater yet.
Salt particles would seed the clouds with droplets less than 1 micron wide.
If you have a large number of small drops, there's a bigger surface area, and this makes them reflect more. The net effect is 2% more of the sun's energy back out to space. And the plan is to have wind-driven vessels cruising backwards and forwards across the wind.
Hundreds of unmanned vessels like these. Those towers that look like smokestacks don't just send up the mist, they spin. And their spin is what moves the ship, using what's called the Magnus effect as they interact with the wind.
If it's spinning like that, there's more air coming along here, going faster, and a little bit being returned back that way. This is exactly the same thing that happens on the top surface and the bottom surface of an airplane wing.
In other words, the spinning rotor creates lift. To demonstrate that, Salter and his students built this rotor, raised it 8 feet off the ground, spun it to 7,000 RPM, and let it go. Instead of plummeting to the ground, it eerily floats across the room because the upward lift is counteracting the force of gravity. Watch again. It only looks like slow motion.
That was great, wasn't it?
Other scientists think there are limits to the plan.
It's only going to work over the remote marine atmosphere. And so you might be able to cool off places in the middle of the ocean, but it's not going to help people in London or Berlin or New York City.
Salter, though, believes the effect would be global.
If the advice that we're getting from the top atmospheric physicist is correct, we really could undo all the damage we've done to the atmosphere since the beginning of the Industrial Revolution.
Salter's isn't the only geoengineering idea floating around.
One idea is to put a bunch of sunshades in space. They would block some of the sunlight from heating the Earth. It's a really nice idea, but you need to build something like a square mile of this satellite every hour and keep that going, for hundreds of years. It's just awfully hard to do.
Ken Caldera of the Carnegie Institution has been studying geoengineering ideas for several years.
The cheapest way to effectively reverse global warming is to inject sulfur high into the atmosphere.
This idea is based on a natural phenomenon.
Mount Pinatubo eruption in 1991 put a veil of aerosol pollution into the stratosphere, and it blocked out the sun.
And the Earth cooled off after that, despite the growth in greenhouse gases. This gave people the idea that, well, we could do this artificially.
The concept is to pump sulfur particles up to the stratosphere with a miles-long hose suspended by balloons and blimps.
You took like 1 bucket of sulfur each second and threw it into the stratosphere. That is enough to reverse the effects of a doubling of greenhouse gases. And all of our simulations and calculations suggest that this will be both cheap and effective. And that's what kind of scares me, because I also think it's very environmentally risky, that if we start toying with our planet, we'll eventually just screw it up.
I would hope that this never needs to be used in the same way that the Strategic Air Command hope that they'd never have to do anything. But I greatly fear that we are going to need every possible way of putting the toothpaste back in the tube.
As our weather gets ever wilder, as the storm fronts grow more intense, scientists around the world are putting themselves on the front lines of climate change. They're trying to understand the changes we face and figure out how to fight back against them. And they're building and using the new technologies that one day just might save the planet.